Hello and welcome to yet another sequences and recurrence relation video. Up till now, we have learned how to solve some basic types of recurrence relations. The links are in the description. Now let us try more advanced one. Here we have sequence an satisfying a1 equals 1 and n sn plus 1 equals n plus 2 sn plus n plus 1 cubed, where this sn is the sum of first n terms of sequence an. So the partial sum. Solve this recurrence relation and find an. Here the most troubling part is of course this sn. But I have already made a video on how we can relate this partial sum to general nth term an. The relation is as follows. Here an is given as sn minus sn minus 1, but only for n greater than or equal to 2. And for the first term a1, we have to obtain a1 from s1. So let us manipulate the given recurrence relation to obtain expressions like sn minus sn minus 1. So we have this, and substituting n minus 1 instead of n gives n minus 1 sn equals n plus 1 sn minus 1 plus n cubed. So we have these, and let's do the subtraction. Then we have n sn plus 1 minus n minus 1 sn on the left hand side, and on the right hand side we have n plus 2 sn minus n plus 1 sn minus 1 plus n plus 1 cubed minus n cubed. And here we have to rearrange bits smartly. So first, this and n times sn, they give us n times sn plus 1 minus sn, and we have this term left, which is plus sn, so that's the left hand side. And on the right hand side, we have n plus 1 sn minus 1 here, so from here, we can take n plus 1 sn, then combined with this term, we can write minus sn minus 1. But this only gives n plus 1 sn, but here we have n plus 2 sn, so we have one more sn. So that's the sn part, and from this n plus 1 cubed minus n cubed, we have 3n squared plus 3n plus 1. So we have this. And notice that sn cancel out, and sn plus 1 minus sn is an plus 1, and sn minus sn minus 1 is an. So we have n times an plus 1 on the left hand side, and n plus 1 an plus 3n squared plus 3n plus 1 on the right hand side. And it's also worth mentioning that we used n minus 1 in this step, and n minus 1 can be natural number only if n is greater than or equal to 2. So n is greater than or equal to 2 is assumed here, and it also applies to this relation right here. So let's keep that in mind. So now we have recurrence relations with only ans. Now where do we go from here? Well, this is the recurrence relation where we rearrange terms to obtain a new sequence Bn. Here, we divide both sides with n plus 1, which gives an plus 1 over n plus 1 equals an over n plus, and 3n squared plus 3n plus 1 can be written as 3n n plus 1 plus 1. So we have this divided by n plus 1. So, letting new sequence Bn be an divided by n, for all natural numbers n greater than or equal to 2, we have Bn plus 1 equals Bn plus, and notice that this divided by this gives 3, so we have 3 plus 1 over n plus 1. Now, if you take a look at this recurrence relation for Bn, you'll know that it is a simple Bn plus 1 equals Bn plus Fn form. And I have already explained in one of my previous videos that we can solve this type by An equals A1 plus the differences fk from k equals 1 to n minus 1. Or equivalently, substitute n with 1, 2, 3, so on, up to n minus 1 and add them up. But for our recurrence relation with bn's, we don't start from b1. We start from b2 because this n greater than or equal to 2 condition from previous steps is preserved. In fact, sequence bn is defined only for n greater than or equal to 2 in the first place. Therefore, instead of starting from b1, we start from b2 and then add up the differences from k equals 2 to k equals n minus 1, which is given as b2 plus sigma 3 plus 1 over k plus 1. Here, let us split the summation into the summation of 3 and the summation of 1 over k plus 1, which can be also written as the partial fraction 1 over k minus 1 over k plus 1. So for the first sigma, we have n minus 2 terms because k is from 2 to n minus 1. So we have 3 times n minus 2. And for the second sigma, this is a telescoping sum. So as you can see, this and this cancel out, this and this cancel out, and so on. So we have b2 plus 3 n minus 2 plus 1/2 minus 1 over n. Now let us find b2 using our original given recurrence relation. When n equals 1, we have s2 equals 3s1 plus 2 cubed. And here s1 is equal to a1, which is 1. And s2 is a1 plus a2, so it is 1 plus a2. So the left-hand side is 1 plus a2, and the right-hand side is 3 times 1 plus 8, which gives a2 equals 10, which gives b2 equals a2 divided by 2, so 10 divided by 2, which is 5. So this is 5. So we have bn equals 5 plus 3n minus 2 plus 1/2 minus 1 over n, which gives 3n minus 1/2 minus 1 over n. Notice that this expression works for n greater than or equal to 2, but not for n equals 1, because b1 is not defined in the first place. So now that we've found bn, which is an divided by n, we can finally find an by n times bn, but only for n greater than or equal to 2. Therefore, we have to write a1 separately, which is just 1. And when n is greater than or equal to 2, an equals this times n, so 3n squared minus n over 2 minus 1. And this is our final answer. And that was all for today's video. Thank you for watching, and I will see you in another video.